So you need to open up your note package to the next lesson, which is called Reciprocal Quotient and Pythagorean Identities, and this is on page 3 of your unit handout. You will also need in front of you today a copy of your formula sheet, so I'll give you a minute to make sure that you have that out in front of you. And we're doing a lot of things today. We're introducing you to begin with to the idea of something called the trigonometric identity. And trigonometric identities, you will learn what they are in a minute, but we're going to be looking at verifying trigonometric identities. And you can verify trigonometric identities, which means demonstrate that they work, using numbers or graphs. We're also going to be talking about non-permissible values of trigonometric identities. And you can make a mental note right now, actually, that when it comes to non-permissible values for anything trigonometric, that occurs, these non-permissible values occur because of division by 0. There are other ways you can get non-permissible values in mathematics, but when it comes to trigonometric identities, we're dealing with division by 0 being the problem. When you go to divide by 0, you can't do that, of course, which means you're not allowed to do that, and that's what non-permissible is. We've already talked about non-permissible values before in other areas in math. If you had an expression of x over x minus 1, 1 is a non-permissible value of x. Because if you were to put 1 into that expression, you'd have 1 minus 1 in the denominator, which is 0, and that's just not allowed. You can't divide by 0. We're also going to be looking at the difference between a trigonometric identity and an equation, trigonometric equation. I'm spending a lot of time going through this because today we are only looking at these 3 trigonometric identities, 3 types of trigonometric identities. Tomorrow we will look at another type of trigonometric identity. And I think for the next few days we're only going to go 1 lesson a day. And then on Friday we're going to look at another type of trigonometric identity. So we're going to be doing a lot with these identities. And then, of course, we're going to be using these 3 types of trigonometric identities today. So as a warm-up, we're going to learn what an identity is. I have an equation there, and I do want you to make a mental note that this statement, 2x squared minus 23x plus 5 equals 77 minus 5x, that's an equation. It's an equation because it has an equal sign. The first thing we're asked to do is verify that the equation is true when we use x equals negative 3. So what that means, and there's a very specific method to doing this, is that you put negative 3 in on the left-hand side, and you put negative 3 in on the right-hand side, but there's no equal sign. The concept of verifying whether something is true or not means you don't start by assuming it's true. So what we have to do here, everybody, is work on the left and the right side separate from one another. So all I've done is wherever there is an x, I've put a negative 3. Wherever there is an x on the right-hand side, I've put a negative 3. So I would like everybody to do me a favor, please, and calculate what you get for the left-hand side, which is 2 times negative 3 quantity squared. If you're going to use your calculator, you're going to have to put the negative 3 in brackets, which I would always recommend for substitution, and then minus 23 times negative 3, and then plus 5. And by my count, I think Well, you guys start typing what you get for the left side in the chat, please. I'm seeing a bunch of 92s. That's good. And what is it you get for the right-hand side? You get 92 as well. So this is not a difficult task. Since the left side and the right side are equal, we have verified that that equation is true when x is negative 3. Now, does 12 make it true? So I'm not going to show my substitution here. I'm just going to write when x equals 12, what does the left side equal? On the right side, when x equals 12, what does the right side equal? And you can work that out for me, please. I'm going to want two numbers here. I'm going to want a number for the left side and a number for the right side. Yeah, I'm getting 17 for both sides. So be very, very careful here. When you put this into your calculator, you have to put brackets around any substitution. Just double check your work because, Keith, I believe it's 17 for both sides. Okay, so we get 17 for both sides. So what does that tell us? It tells us that the answer to this question is yes. X equals 12 makes this equation true. So you did end up getting 17, Keith? I'm assuming you did. No worries, and that's a very simple thing to forget. Now, is the equation true for all values of x? This is a really weird question. Because if it is true for all values of x, this is bordering on philosophy. If it is true for all values of x, you could never demonstrate it because you can never put every value of x in. But let me write down the equation so that I can see it. It's 2x squared minus 23x plus 5 equals 77 minus 5x. Well, let's try something. Let's just pick another number. And I think a really easy number to work with is 1. Let's try 1. If I put 1 in for x on the left side and 1 in for x on the right side, what kind of answers do I get? Well, on the right, I have 77 minus 1, I have 77 minus 5, which is 72. And on the other side, I have 2 minus 23 plus 5, I believe, but I'm going to want some verification here, that the left side is negative 16. Okay, good. So what I said was, if it is true for every value of x, we can't demonstrate that. But if we find even one value of x for which it's not true, then we know that the equation is not true for all values of x. So the answer to this question is no. That equation is not true for all values of x. Let's take a look at the next part of the warm-up. Now let's look at this equation. X plus 5 quantity squared plus 37 equals x squared plus 10x plus 62. Is it true when x equals negative 3? Let's see. Negative 3 plus 5 quantity squared plus 37. And over here we have negative 3 quantity squared plus 10 times negative 3 plus 62. Take a minute, please, and when you get what the left side is equal to, let me know. And if you get a different number for the right side, then type left side equals, right side equals. If you get the same number for both sides, just type that number. Yeah, it's 41 for both. So we've verified that it's true. Well, we knew it was going to be true because the question says to verify it. So we're done. It's true. It's true. The equation is true when x is negative 3. What about 12? Well, let's try it. 12 plus 5, quantity squared, plus 37. 12 squared plus 10 times 12 plus 62. Aaron says 326. Marissa says 326. Again, I've said this before, math is not a democracy, but assuming that we're all getting 326, it's correct. 144, 17, yep, 326. So 326, 326. The answer to this question, does x equals 12 make it true, is yes. So I want to go back to number 1 because this is an important distinction. In number 1, that equation was true when x was negative 3. And that equation was also true when x is 12. In question 2, this equation is true when x is negative 3, and it's also true when x is 12. Is this equation true for all values of x? Well, okay, let's try some. Let's try putting in 0. You know what? Rather than putting these numbers in, why don't we put this in for y1 and this in for y2, and don't look at a graph, look at the tables. So I'm going to put in for y1, and again, I'm not interested in a graph. That's not the point here. For y1, I'm going to put in brackets x plus 5 n bracket squared plus 37, and then I'm going to have x squared plus 10x plus 62. Double check to see that I've entered them correctly. So I'm going to my table. Now my table is probably set up to be on automatic, which means it starts at 0 and goes up by 1. And when I look at my table, when x is 0, I get the same thing for the left side and the right side. And I can scroll around all I want, and that is true. Now what if, and again this is bordering on philosophy, what if there's a decimal number that doesn't make it true? Well, what I can do is set up my table by choosing second window and scrolling down and selecting independent ask by hitting enter. What this does is it clears my table, and now I can put in any number I want for x. I can put pi in for x, and I get 103.29. I can put negative 36,555.21102, and I get the same number for each side. But theoretically, everybody, I haven't proven to you that it's always true. It turns out it is. But there could be a number for x that I haven't thought of that makes it not true. So the best we can answer here for C is, it appears so. And I will put the true answer in brackets. It turns out that that equation is true for all values of x. By the way, I'm going to show you a proof of why that equation is true for all values of x. If you look at the left side, it's x plus 5 squared plus 37. Let's not put anything in for x. Let's just simplify that. Aaron?
If you expand it out, it's going to be the same thing.
Yes, that's what I'm getting at. Is that what you were asking in the chat room?
Yes.
Yeah, but see, some people might not see that. You know, and I didn't spend a lot of time disguising these two things, but yes, that's the point here, is if I expand out x plus 5 squared, which is x plus 5 times x plus 5, and I add 37, I'll get x squared plus 10x plus 25 plus 37, which is x squared plus 10x plus 62, which is what we had on the right-hand side, which means we didn't put numbers in. It means the left side is always equal to the right side, and that's what we call a proof. You know, it's an algebraic proof because there's no trig, but we will get to that later. So now, an equation is a mathematical statement that relates or equates two different algebraic expressions. If you look in warm-up 1, that was an equation. If you look in warm-up 2, that was an equation. What an identity is a specific type of equation. An identity is an equation that is always true. So an identity is a subset of equations. If I were to draw what's called a Venn diagram where everything in here represents equations, then inside of this are a subset of equations called identities. It's like me doing this. All chickens are birds. Not all birds are chickens. That's not what I'm saying. All chickens are birds. All identities are equations. But not all equations are identities. An identity is an equation that's always true. So, for example, this is an identity. Now let's show that this is always true by looking at it in our graphing calculator. So I would like everybody to enter the left side in for y1 and the right side in for y2. And we are going to reset our calculator table features to be on automatic. So you're going to go to your table setup, which is second window. Let's start at 0 and go up by 1 and make sure it's on automatic. So we go to my table and we look, hey, they're always equal, they're always equal, they're always equal, except, wait a minute, they're not always equal, are they? There is a value of x, when x is 2, where the left side and the right side are not equal. I want you to note that that value of x, where they are not equal, is a non-permissible value. I don't know how that's spelled. Sometimes I spell it with an A here, sometimes I spell it with an I. I don't know. And if you look at the previous page here, it says an identity is an equation that is true for all permissible values of the variable. So it may not be true for a non-permissible value, but as long as it's true for all permissible values, then it's an identity. How many of you, by the way, see, just type yes in the chat, how many of you see that these two are always equal except for that non-permissible value by looking at the algebra of what this is? Let me give you a hint. Is x squared minus 4 factorable? Well, x squared minus 4 is a difference of squares. So we can cancel the x minus 2's and be left with x plus 2. They're exactly the same thing. It's like me giving you the following and asking you, is that an identity? Well, yeah, of course it's an identity. Okay, so that's what an identity is. What do we learn from this warm-up? This first equation, which is 2x squared minus 23x plus 5 equals 77 minus 5x, is not an identity. Correct me if I'm wrong, that was the equation that was not always true. Yes? Okay, good. The equation x plus 5 quantity squared plus 37 equals x squared plus 10x plus 62. This should be is not an identity. Is an identity. Examples of identities are the things on the left. Now, we won't talk about the trigonometric identities just yet, but it turns out that this statement here, this is always true, well, except when x is a multiple of pi over 2, because when x is a multiple of pi over 2, tangent of x would be undefined, okay? But that's always true. It turns out if you were to figure out sine of 1.2 radians over cotangent of 1.2 radians, and then you figured out tangent of 1.2 over cosine of 1.2, you'd get the same number. I hope you can see how this is always true. It's a very simple identity because if you square x plus 2, of course you get x squared plus 4x plus 4. Some of these other ones are not identities. So the idea again here is if you put in a value for x into the non-identities, you'll be lucky if it's true. It probably is not going to be. Okay, so what about this equation? Sine of x equals cos of x tan of x. What are the non-permissible values for x? I told you at the beginning that non-permissible values happen because you divide by 0. And in order for me to make this a little bit easier for some students, what I'm going to do is rewrite this equation as sine of theta equals cos of theta tan of theta. So that's what I'm thinking of here. Now, what are the non-permissible values of theta? Theta is not allowed to be certain things. Why? Well, because there's a tangent of theta in here. And on the unit circle, tangent of theta is y over x. That's the definition. Now, where would this be 0, which is not allowed? Well, x equals 0 on the unit circle, here and here. So whenever the rotation angle terminates at the top or the bottom, tangent is not defined, which means theta cannot be something like pi over 2 or 3 pi over 2. And you can check this out on your calculator right now. Go ahead and try to take the tangent of pi over 2. You get an error. It calls it domain error, but it has nothing to do with domain. Don't worry about that. If we try 3 pi over 2, you'll get the same thing. So going back to the question and talking about the reality of the question, it wasn't theta, it was x. So x is not allowed to be those numbers. Again, I hope you understand that this x here is actually equivalent to the theta. And the x on the right-hand side, this x, is not the x in the equation. It's the x on the unit circle. Given that there are an infinite number of angles that end up in those not allowable positions, we have to say that it cannot be pi over 2 plus multiples of pi, where n is an integer. And we're not going to get hung up on non-permissible values today. I introduced them a little bit in this lesson so that we can figure them out better later. Verify that the equation is true for 40 degrees. We're not going to Sorry, I have a little bit of a tickle in my throat, so if I turn my mic off, it's because I got to clear my throat and cough. We're not going to do anything in terms of showing work for question B here. We're simply going to figure out what the sine of 40 degrees is. I'm in degree mode. The sine of 40 degrees is that number. And I'm going to figure out what the cosine of 40 degrees, close brackets, multiplied by the tan of 40 degrees is. And I get the same number. So we've verified that it's true for 40 degrees. Verify that the equation is true for all permissible values of x. Well, here is where we use the tables. What we want to do is look at this as being y1 in the tables, this as being y2 in the tables, and look at whether the numbers are equal for all non-permissible values of x. So y1 is sine x, y2 is cos x tan x. I'm in degree mode, but quite frankly, who cares? I'm going to go to my table and I'm going to look at y1 and y2 for all of these different angles. And I can see that they are always equal, except, and this is going to take forever for me to scroll, so I'm going to start at 82 degrees, except that they're equal, they're equal, continue to be equal, and then at 90 degrees you get an error on one side. Well, that's okay. That just means 90 degrees is non-permissible. So we've verified that it's true. I would like to show something to you, though. Let's graph it. So I'm going to go zoom trig. Okay. Here comes sine x. And now here comes cos x tan x. But you notice that we don't see it, right? Because it's right on top. Let me show you, though, that it is on top by going back to y. And I don't know if you've ever done this. Scroll over to the left of y2. And if you hit enter one time, it graphs a thick line. I don't want that. If you hit enter again, it does something called shading, again shading. I want what I call the little bouncy ball. Now when I hit enter, it's going to graph that second graph, and when it does, it's going to trace it with that bouncy ball. And I want you to watch it carefully. Here's the first, and here comes the second. But you will notice that any time that bouncy ball gets to a non-permissible value, the calculator stutters. There's a little mark left because it doesn't know what to calculate. And those are the non-permissible values. So is it an identity? Yes. We haven't proven it, but we can say that it is. Any questions with that example? Too fast, too slow, or just right? Thank you. All right, so now we're going to talk about specific identities. And this, for many students, is going to require an extra amount of extra work. Like this, some people will pick up on these identities very quickly and they'll work with them, and others struggle. You have to work hard at this. So we're looking at what are called reciprocal identities, quotient identities, and Pythagorean identities. These three identities, which we've never called identities, are true. They're always true. If I go into Wolfram alpha, so you don't have a cosecant button on your calculator, right? So if you put this into your calculator, you're going to have to put 1 over sine of theta. So you're going to be putting that for y1 and this for y2. Well, Of course they're going to be equal. But Wolfram Alpha is a mathematical website which will allow you to enter in any mathematical expression you want. So I'm actually going to, did they say Wolfram? What happened there? I'm going to actually duplicate this window, and I'm going to put cosecant of 4.2. And I can see that it gives me negative 1.14734. The cosecant of 4.2 radians is this number. And if I were to type in here 1 divided by sine of 4.2, I get the exact same number. When I put these two side by side, find the other one, there it is. Cosecant of 4.2 is that number. 1 over sine of 4.2 is that number. What if I put cosecant of x? I could put theta, but I don't want to be that fancy. And 1 over sine of x. Well, what does the graph of cosecant of x look like? It looks like this. What does the graph of 1 over sine of x look like? It looks like the same thing. What's an alternate form of 1 over sine? It's this expression here. Well, that's the same as an alternate form of cosecant. What I'm getting at is that you have to take our word for it that these things that we've already talked about in this course are always true. Okay? Now there's more identities. Oh, by the way, you have to know the names of these. These are called reciprocal identities because they involve a reciprocal. There are what are we calling the quotient identities. Quotient means divide. So tangent of theta is always equal to sine of theta over cos of theta. If you take your calculator, and you can try this on your own, I believe I happen to be in degrees, so we can stay in degree mode if you like. I'm going to take the tangent of 68.2 degrees, and I get this number. If I take the sine of 68.2 degrees and divide by the cosine of 68.2 degrees, I get the exact same number. Tangent, I'm at my computer with a mouse here, so it takes me a little while. Tangent of theta is exactly the same as sine of theta over cos of theta. They're always the same. And it turns out that since cotangent is the reciprocal of tangent, cotangent is cosine over sine. And then we have the Pythagorean identities. Now this first one, you already knew. And the reason why you already knew that one is on the unit circle, sine is y and cosine is x. But you know x squared plus y squared equals 1 on the unit circle. There are some other ones. 1 plus tan squared equals secant squared. 1 plus cotan squared equals cosecant squared. So now that I've filled your brain with, I guess, 8 different identities that we're learning today, I can draw your attention to your formula sheet, and on your formula sheet, they are all there. I've blocked out some other stuff that we'll deal with later. And I've added in the names of these. You do need to know these names. These are the quotient identities. These are the reciprocal. And these are the Pythagorean. So before we get started today with working with them, they are on your formula sheet, so you don't need to memorize them. But you need to get used to recognizing certain identities. Okay? So for example, this identity right here, sine squared plus cos squared equals 1, it pops up in math a lot. So if you're ever working on something, no matter how complicated it is, and you end up seeing cos squared plus sine squared, feel free to rewrite it and just put the number 1 in there. I'm going to ask you a question now. I need to know, and I should have written this down. That whole package of materials I gave you, is there a single pink sheet in there that says something like when working with identities? There is. Does it say when working with identities, or does it say when proving identities? Good. So I'm going to be referring to that from time to time, so you will want to have that out as well. All right, let's take a look at some questions now. The first thing is verify that that's true for the following values of x. We can do this with a graphing calculator. Again, sine squared plus cos squared equals 1 is the most popular of the identities. I can take the sine of 52 degrees and square that, plus the cosine of 52 degrees and square it. I get 1. If I do the same thing with what we were asked to do, which I didn't read the question, is 40 degrees. I get 1. If I do it with 5 pi over 6, I guess I should be in radian mode. And I take the sine of 5 pi over 6, and I square the sine, and I add the cosine of 5 pi over 6, and I square the cosine. I get 1. So sine squared plus cos squared is always 1. Prove this identity. Okay. On Friday or Monday, I haven't decided, we will have a lesson on proving identities. But it's tough to prove identities. It's tough to learn how to do this. So I'm starting off with every now and then in our lessons having a proof. I want to take you back in time here to when I think Aaron had even said, aren't these two the same? This was the one, yeah. Aaron had typed something in the chat about, aren't these two the same anyway? And I said, yes. And I proved it to you. Look how I proved it. I manipulated the left-hand side until it matched the right-hand side. Now, I could have manipulated the right-hand side to match the left-hand side. But this line down the middle is crucial to a proof. So that's what we are about to do with this trigonometric expression. We're going to draw a line down the middle. We're going to put 1 plus tan squared of x on the left side and secant squared of x on the right side. And when you prove an identity, you manipulate one side so that it's identical to the other, or you manipulate the other side so it's identical to the first, or you maybe meet them both ways, meet them halfway. Now, we can't use this identity. If you were to look at your formula sheet, you'll see this identity. We're asked to prove that these are the same thing using other identities. So the first thing I'm going to do is this. And I want everybody to think long and hard about how I got from 1 plus tan squared to 1 plus sine squared over cos squared. And if you feel you could explain it, feel free to type in an explanation in chat, or feel free to unmute your mic and explain to me how I'm allowed to do that. Okay, so here's Chloe's response. Chloe said sine of theta is y and cos of theta is x and tan of theta is y over x. So what Chloe has said is, since I'm going to write this out so everybody can see it so you don't have to look at the chat, what Chloe has said, and it's perfect, is that sine of theta on the unit circle is y, cos of theta on the unit circle is x. You're told that tan of theta is y over x, but y is sine of theta and x is cos of theta. So, and then Aidan McDonald put because tan equals sine over cos. And I want you to notice that that's the exact same thing that Chloe said, except I believe Aidan is saying that because he's looking at his formula sheet. And Aidan, you can let me know if this is the case. Aidan looked at the formula sheet and said, well, tangent of theta is the same as sine over cos. Yeah. And you know what? From now on, tangent of theta equals sine of theta over cos of theta should be as obvious to you as 2 times 3 is 6. It's one of those identities that you just know. Now, this is called a quotient identity. And what we need to do, going back to our proof, what we need to do is write down the reason we did that. We have to actually write down quotient identity. And I get what most of you are thinking right now. Most of you are thinking, are you kidding me? And that's exactly what I was thinking way back when Mr. Von Holland, my Math 30 teacher, put this on the chalkboard back in the old days. I went, you mean we have to write words down for math? Yes. Okay, now I want you to take a look at that sheet, that pink sheet that's in front of you, that's a series of strategies. When you look at the first strategy, it says write everything in terms of sine and cosine. Well, that's what we just did. The first point on that sheet says write everything in terms of sine and cosine, and I did that. And you know what? Maybe while we're at it, let's do the same thing to the other side. I'm going to put 1 over cosine of x. Oh, by the way, if tangent of x is sine over cosine, tangent squared is sine squared over cos squared. So I'm going to put here 1 over cos squared of x. Why am I allowed to do that? And you don't want to think unit circle here. You want to think identities. Why am I allowed to put secant of the rotation angle? It's the reciprocal identity, yeah. The reciprocals. We go to our formula sheet and we can see that we have used a reciprocal identity, so we write that down. Now, I'm not sure what's next on that list, and I'm not going to take time to pull up that document. But somewhere on the list it says if you have multiple fractions, bring them together with a common denominator. Can I get somebody to confirm that there's an item on the list that says use a common denominator to bring fractions together? Where is it on the list? Is it second, third, fourth? Fourth. It's way down there. But we're going to do that. The common denominator here would have to be cosine of x because we have 1 over 1 here. So I need to convert this to a common denominator of cosine squared of x. Well, the top of this second fraction is sine squared of x. I'm going to need to multiply the top and the bottom of the first fraction by cosine squared of x to turn it into a denominator of cosine squared of x. when I do that, what I get in the numerator is cosine squared of x. You do not need to use words to explain that. You only need to use words when you use an identity. So now I add these together. The rule for adding fractions together that have a common denominator is you maintain the denominator, and then you add the numerators together. And I have a question for you, even though we're not done. Wow, we're so close to being done. My question to you is, even though we're not done, how many of you see that 1 over cos squared is exactly the same as what we have currently on the left-hand side? Oh, how many? Yeah, I can see your hands. Type yes if you see how those two are equal. And what should be happening over the next few days is every time I ask a question like that, it should be quicker. It's not a race, but there should be more and more people saying, well, of course they're equal. And they are equal because 1 is what the numerator is, and what is the name of the type of identity that we're using to go from sine squared plus cos squared to 1? Well, it's a Pythagorean identity. When you look at your formula sheet, on your formula sheet is this statement. Can you help me out here? Does your formula sheet have thetas or x's? Theta. I missed my x over here, by the way, with my cos squared. So sine squared of theta plus cos squared of theta equals 1. That's all we're doing. And now what you do at the end, this is really weird, but you have to do this. At the end, now you write left side equals right side. That's a proof. There's a lot to take in there. If we take a look at all of the work, we did a fair amount of work. Does anybody have any questions with example 3? All right, let's take a look at the next example. Simplify. I have a question for you, and don't feel bad if you don't know the answer immediately. I'm just finding out where everybody is, and I want everybody, if the answer to the question is yes, to please type yes in the chat. How many of you see almost immediately that this is sine squared of x? That's a pretty large number of you, and that's really impressive. What you are hopefully seeing is when you see that tangent, the goal is this. When you see tangent of theta without even looking at a formula sheet, you see sine of theta over cos of theta, which means that if I were to square both sides of that identity, I would get tan squared equals sine squared over cos squared. So I am getting, I don't know why that yellow thing is there. I am getting when I rewrite this using sines and cosines, I am getting sine of x quantity squared over cosine of x quantity squared multiplied by cosine of x quantity squared. Look at how I wrote it. I didn't write it this way. I didn't write sine squared of x over cos squared of x times cos squared of x. Don't do that. Line things up, because then you can see they cancel, so you're left with sine squared of x. I'll be honest with you, I really don't care about non-permissible values for any of the stuff today, okay? Let's not worry about that. It's going to eat up too much time. Cosecant times secant over cotangent. Now, I hope you remember yesterday and today when we had something like this, that I said, yes, you could multiply by the reciprocal to simplify, or you could do this. And I told you that doing this, multiplying the top and the bottom by denominators to get rid of, is a wiser move. It's a better tool because it's used all the time, not just when you're dividing by a single fraction. Let me show you what I mean. I'm going to rewrite this as on the top 1 over sine of theta times 1 over cosine of theta, and on the bottom cosine of theta over sine of theta. And since we're not proving this, we don't need to write down the reasons why, but I would like you guys to start typing the reasons why. We'll do this one at a time, actually. What is the reason why I was able to go from this highlighted yellow part to this highlighted yellow part? Why am I allowed to do that? Even though we don't have to do this in this question, I want to know if you know why. Sure, reciprocal identities. Cosecant is 1 over sine. Secant is 1 over cosine. Now again, I'm going to write that down, but you don't have to in doing your work unless it's a proof. And yeah, those highlights make sense. Now, what is the reason why I am able to go from cotangent of theta to cosine of theta over sine of theta? Well, quotient identity. Perfect, Sarah and Aaron and Katya and Aiden. I mean, you have to know the names of these. So the identity that we're talking about there for the blue transition is a quotient identity. But how is this helpful? So I've made a mess of this right now. I'm going to rewrite it. We have 1 over sine of theta times 1 over cosine of theta over cosine of theta over sine of theta. And this sine of theta here makes me unhappy. This cos of theta here makes me unhappy. And this sine of theta on the bottom makes me unhappy. I'm unhappy because I have what's called a complex fraction. I don't like to have denominators. There's a denominator here of sine of x. I don't like to have a denominator of sine of x or cos of x in the numerator, and I don't want a denominator of sine of x in the denominator. I have to get rid of these three things, and I'm going to do so by multiplying the top and the bottom by whatever it takes to get rid of them. Right? If you were writing a diploma exam and you put little unhappy faces, that's fine. A person might kind of get what you're doing, but it's not part of your work. How do I get rid of over sine of theta? I multiply by sine of theta. So I'm going to multiply the top by sine of theta and the bottom by sine of theta. By the way, notice that when I do that, I will eliminate the sine of theta on the bottom as well. But I will still be left with this pesky cosine of theta, which I'll just highlight temporarily. I'll still be left with that, which I got to get rid of as well. I have to get rid of that as well. So I'm going to multiply the numerator and denominator by cosine of theta. And now I can finally say to you guys something that's important at this level. whenever you are working with algebra, work from the top of the page to the bottom. Do not go equals, equals. Don't go left to right. There's a reason for it. I don't want to get into the philosophy of math education, but there's a reason for it that makes your life easier. So what happens? Well, canceling is what happens. Sine, sine, cos, cos. These are all multiplied together. So we can cancel wherever we want. Sine, sine. So what do we have left? We have on the top 1. All we've got left on the top is 1. And on the bottom, cos squared of theta. Which means that this original expression of that, I'm not even going to say it, is equal to 1 over cos squared, and on an exam, the multiple choice might be secant squared of theta. I hope you see how 1 over cos squared and secant squared are the same. Any questions with that example? Can you take a look at that pink sheet that I've given you, and can you let me know, and I'll print one out for myself for tomorrow, but can you let me know, does the final thing say, if things get too messy, go back and start again? Okay, so here is my analogy, and I've used it for a long time. Some of this stuff is pretty ugly to begin with. Look at this. That's ugly. So what happens sometimes with math students is they freeze. They sit there and they stare at this and stare at it and stare at it. But I've given you some tips and tools to follow, and you have to try it. My analogy is this. If all of a sudden, you were kidnapped in a foreign country and you broke out of wherever they were holding you and you ran out of the forest and you were on a dark road, you're not just going to stand there. You're going to start to go someplace. But you're going to start taking steps towards what you hope is your destination. If the road gets narrower and narrower and darker, and you start to hear growls coming from the bush, then you're going to go back to the beginning and try something different. But you have to try something. All right, let's take a look at C. One of the things on that pink sheet will say, keep an eye out for known identities. But the very first thing I think is the best thing to try is the first suggestion. Give some thought as to why I am allowed to do this. So I'll start with this question. Why am I allowed to go from cosecant squared to 1 over sine squared? Sure, it's a reciprocal identity. Why am I allowed to go from cotangent squared, from cotangent squared to cos squared over sine squared? Yeah, it's a quotient identity. So I'm asking you these questions again and again because I want to get you familiar with okay, and on the top we have 1 minus cos squared. Not everybody's going to get this the first time or even the second time. But how many of you see that this whole thing is equal to 1? I'm going to let you stew on that for another 30 seconds or so. Okay, so turn your brain off of that question for a second. Don't try to connect what I'm about to describe to you to the question just yet. Type into chat what sine squared plus cos squared is equal to. Well, we know that, right? We know that. I mean, that's, man, if we ever see that, that's 1. Shouldn't even have to blink. We know it. But if this is true, if I subtract, just for kicks, I'm going to subtract cosine squared from both sides. So what does that give me? Well, I'll have left on the left-hand side sine squared of theta equals 1 minus cos squared of theta. So what I am telling you right now, and I know the burden is huge, and I'm not being sarcastic. I'm saying I'm asking a lot of you. What I'm asking you is, now that you know whenever you see sine squared plus cos squared, you can replace it with 1, I'm asking you to know from now on that whenever you see 1 minus cos squared, you can replace it with sine squared. And by the way, I could also, if I take that original Pythagorean identity and subtract sine squared, have cos squared of theta equals 1 minus sine squared of theta. And I guess maybe a way to look at this is to say that this identity here, which is on your formula sheet, is actually 3 identities. It's sine squared plus cos squared is 1, sine squared equals 1 minus cos squared, and cos squared equals 1 minus sine squared. So, and now I have more experience than you, I know that, but when I see this thing, I immediately say the top is sine squared of theta because 1 minus cosine squared is sine squared. This is the same as this because 1 minus cos squared is the same as sine. And we're left with then, I don't like what I've just done there, so let me get rid of it. What we're left with is sine squared on the top and sine squared on the bottom, which means we're left with 1. At the very end, it's okay to go left to right, I think. Any questions with that example? You can see why I hope that we're only doing 1 lesson today, and this is going to continue for a few days. The very first thing I've said to you is write everything with sine and cosine. Well, that's already done. One of the things I've said to you is to keep your eyes peeled, keep your eyes open for known identities. So for example, if I saw cosine squared of x plus sine squared of x here, I'd replace it with the number 1. I don't see anything here that's popping out as being part of an identity that I know. One of the things I've got there, and we haven't encountered it yet, but we will, is to factor wherever possible. And there's nothing to factor here, but I do see that I have 2 fractions, and I'm going to put them together with a common denominator. The common denominator here, everybody, is going to have to contain a 1 plus cosine of x. Do me a favor and put brackets around the 1 plus cos of x and the sine of x in the top, and a sine of x. Common denominators must always contain every single factor in all of the denominators that you're bringing together. So there's no way for us to get anything simpler for a common denominator. That's what it is. You may have to, and I just want to check my handout here to find out. Yes. You're going to have to rewrite this before you do what I said so that it's spaced out. You'll see why in just a second. But you are going to want some room here and some room here. Here's the reason. In order for me to convert 1 plus cos x as a denominator to 1 plus cos x times sine x, I have to multiply the top and the bottom of this first fraction by sine x. So I need room to write that. I should have spaced it out more for you on the handout. And I also need to have room to write what I need to multiply the top and the bottom of the second fraction by. The second fraction has a sine x already, but I need to have sine x and 1 plus cos x. This has nothing to do with identities yet. I'm just bringing things together with a common denominator. So I need to multiply the numerator and denominator of this by 1 plus cos x. So what we end up with on the top is sine squared of x, and then we have plus cos of x times 1 plus cos of x. I want to pause there. Any questions with that first step? One of the questions that you might have, but it hasn't occurred to you to ask it, is, how do you know to do that? Well, that's what that list of strategies is for. You have to start walking to get off of that road. You have to start doing something to work towards the answer. And one of the suggestions was find a common denominator. Now I'm going to give you a tip here. The bottom, you always leave in factored form. If you take calculus with me next semester, this will become a very important rule for rational expressions, for fractions. You leave the bottom in factored form. The top, however, you simplify. So I'm going to take this cosine x and multiply by 1 and multiply by cosine of x, which will give me cosine of x plus cosine squared of x. Any questions with that step? All right, I have a question for you, and I'm going to give you guys a full minute here to think about this. Type yes in the chat if you see that this expression is equal to 1 over sine of x. This is like that old expression, it's always darkest before the dawn. Like, look at where we're at right now. We are at, sorry, I'm sitting at my computer again. We are here. And when you look at that, that's pretty ugly, isn't it? It really is ugly. So you're on that road, you're starting to shiver and you're scared because you don't know if you'll make it home. But it turns out, and those of you that have seen this, it turns out that you just need to take one more step over the hill and you can see the daylight. Because 1 over sine is vastly simpler than this thing. That's what that analogy is about. And I will answer the question in a second, but the analogy is you often don't see how simple it becomes until you take that final step. But you can't freeze in place. You have to go back to that list. So if you go back to that list now, one of the things it tells you to do is to keep your eyes peeled for known identities. And there is, on the top of this fraction, sine squared of x plus cos squared of x. And sine squared of x plus cos squared of x is 1. In other words, I can rewrite this top as sine squared of x plus cos squared of x plus cos of x. So I've rearranged the order in which you write these. By the way, if you see how the top becomes 1 plus cos of x, you don't need to do this. I have rearranged the order of these, and this is now over 1 plus cos x times sine x. Well, the top is 1 plus cos x. I don't think this little bridge is doing anything for us. The top is 1 plus cos x. You should recognize sine squared plus cos squared is 1. So we get 1 plus cos x on the top. That's the only factor of the top. On the bottom, we have 1 plus cos x, and we have sine of x. 1 plus cos x cancels. If I ask a student, what do we have left on the top, and they answer nothing, I ask them, are you sure? You got to have something there. We're left with 1 when you cancel. So you end up with 1 over sine of x, or cosecant of x. So what does a typical multiple choice question look like? Maybe something like that. And sorry, you have to go through all of that to determine that it is, I think we got cosecant of x. This is not easy for some people. All of these problems that are attached, 1 to 15, deal with the quotient identities, reciprocal identities, Pythagorean identities. They start off with simple stuff like verifying. I don't think you need to really spend a lot of time on your calculator verifying. I'm more interested in you doing questions like 3. Well, you know what? Don't do 3. In fact, don't do 3. It's just going to cause confusion because it's not really clear what it's asking, and I don't want to have to explain it again and again. That sounds like I'm being lazy, but it's not important. 3 is unimportant. Don't do it. So really, it's stuff like number 4. Like, can we write this simpler? Well, I mean, yeah. What about this one? Secant is 1 over cos. Sine squared. Cosecant is 1 over sine. So what we end up with this question is, on the top, sine squared of t, which is sine t sine t. On the bottom, cos t sine t. The answer is tangent t. This is what you have to practice. And that pink sheet is your map to success. You have to follow those strategies. So I would say question 4 through 15, like there's a lot of questions here, a lot of just multiple choice. Some are quick, some are long. And tomorrow, I have an appointment tomorrow afternoon, so I have to be gone by 2. So what I'm going to do is do the next lesson tomorrow, and whatever time we have left before 2, I'll go over questions from this section. We're only doing one section on Friday as well, so we will have time to go over questions from this section then. So I'll let you get started. If you have questions, of course, let me know, and I will do them up here on the smartboard.